Welcome to the lesson on arrays. The array is the base structure for much of this course. In this lesson we learn one big idea. When we store elements back to back in memory, finding element I turns into computing its address. We will see how that gives fast, direct access. We will also see why editing the middle is slow. Along the way we meet the core operations and the address formula. Let's start with why arrays matter. The next slides show what the array lets you do, and how the way we lay out data decides if access is fast or slow. This is what you will be able to do after this lesson. You will explain the contiguous layout and say why the elements sit back to back. You will compute an element address by hand, using the formula of the address of A of I equals base plus I times size. Of T, you will reason about the core operations. Access, update, traverse, insert, and delete, and their cost. You will see why editing the middle is expensive, because insert and delete must shift the other elements. And you will search an array, both linear search and binary search, in C. One idea drives the whole lesson. When elements are stored contiguously, finding element I turns into computing its address. Every strength of the array and every weakness comes from that one decision. This is the path we take through arrays. First, what an array really is, a fixed row of numbered slots. Then the array's own operations, the things it promises to do. Next, how an array sits in memory as one solid block, so an index turns into an address. After that, we read any slot and walk across every element. Then we insert and delete and see why changing the middle is slow. Then we search, first a simple scan, then binary search when the data is sorted. And we finish with the cost of each operation and the common bugs to avoid. Suppose a program stores 5 million readings. A user jumps straight to reading 4,832,109. How fast we reach it depends on how we stored the data. Look at the step-by-step panel on the left. Here the data is scattered, so we follow links. We take one hop, then another, until we arrive. The cost grows with the index. In big O terms, that is big O of n. Now look at the direct access panel on the right. The array stores elements back to back, so we compute one address. The base address plus the index times the element size. That is one calculation. In big O terms, that is big O of 1. So arrays give you direct access. You compute the address of A of I straight from the index, but remember one cost. Editing the middle still moves the neighbors.